Hello everyone. Welcome to the final session of the Chain Fusion Educate Bitcoin edition, hosted and powered by ICP. Today we're going to be hearing about how to use Chain Fusion as a cross-chain infrastructure from zCloak network. I'm just going to invite them onto the stage so we can share the presentation as well. Nice to see everyone in the chat as well, GM. Also, small reminder that after this Educate series, there was also going to be a hackathon following up, which we would love for you to take part in and be on our website very soon, so watch out for that one. Hello, welcome to the stage.
Hello, Emma. Good to see you. Hello, everyone.
Nice to see you too. Please ask your questions in the chat as well, and I'll be in the background if you need anything. Stage is yours.
Okay, thank you. So I will start sharing my slides with everyone. Good. Okay, thank you. Thank you for having me for this presentation on Chain Fusion from ICP. So a little bit of introduction about our project and myself. My name is Xiao Zhang, founder of zCloak Network. So zCloak Network is a project that aims to solve the trust and the privacy issue in the age of AI. And what we do is to use decentralized identity, zero-knowledge proof technology, and also Chain Fusion from ICP to deliver these goals. And the recent product from zCloak Network is called the Cloaking Layer. It's a universal ZK verification infrastructure built on top of ZKP. And our slogan is to democratize ZK for everything and everyone. So this product is built using all the benefits that is provided by the ICP Chain Fusion technology. And I can't wait to dig in with everyone to see what we have done. So the contents for this presentation would be a little bit of recap about the Chain Fusion concept from ICP. And for today's presentation, I'm going to focus a little bit on the use of Chain Fusion for zero-knowledge proof and for public blockchains like Bitcoin and Ethereum. So we're going to talk about the zero-knowledge proof verification problem and our solution. We are going to talk about our product, the Cloaking Layer, its architecture, its use cases, and the advantages that it brings. And I'll also show you the roadmap of this product and show you a small and quick demo on how to do a privacy preserving transactions using the Cloaking Layer. Okay, so I think we have been running along the Chain Fusion series, and I have seen awesome videos and presentations given by other speakers. I know everybody must have heard the Chain Fusion concept many times. So here is just a quick recap of what it is about. So from my personal understanding, I think it's an awesome technology. Basically, it allows you to read and write a public blockchain in a decentralized way. That is what ICP offers with Chain Fusion. The key components, if I see it, is that we have these two very unique capabilities provided by Chain Fusion. One is to read and one is to write. For reading, what it means is basically we know that there is Bitcoin full node that is running in ICP. That means we can read all the states, all the UTXOs from the Bitcoin network directly from ICP network. And also for networks like Ethereum and other layer 2 blockchains, we have something that we call the EVM RPC, which can be accessed within ICP, and it works via the HTTP as outcall functionality of ICP. So basically what this offers is for developers in ICP to access states in other blockchains in a decentralized manner within ICP. So this is basically what we mean by read in Chain Fusion. And when it comes to writing, there's this very unique capability provided by ICP. It allows a threshold signature, specifically ECDSA or Schnorr signature, to be generated at the protocol level, which means basically the canisters or the smart contracts in other chains. So these things can actually generate the signatures, and the signatures can be a signature of a transaction, of token transfer, or an execution of logic in a smart contract. And the signed transactions from ICP can be broadcasted to other networks via their own RPC port, and to execute a token transfer, for example, in another network. So basically, we're effectively writing to the other blockchains to carry out logic in their side. So yeah, this is a quick recap, I think, for the Chain Fusion technology, reading and writing. And it has a lot of use cases. We know that we have this native Bitcoin integration within ICP called zkBTC. I personally am using it. I think it's a very nice feature. It provides this safe and fast BTC integration. And you can just transfer zkBTC within ICP very conveniently to a friend, and saves a lot of gas fee, and also it's blazing fast. So it's a great feature. We also can use Chain Fusion as a co-processor for other chains, which means basically you can read the states from other chains and perform complex logic or data-heavy computations within ICP, and then write back the results using threshold signatures. So this is a very powerful pattern that is provided by ICP. In that ICP, we know that it has a very high performance for computation, and it's very economic when it comes to data storage. So with these features combined, basically you can offload very heavy computation from other chains into ICP, do the processing, and then write back the results. So basically the ZK verification we're talking about in this session used this co-processor pattern to do the calculation and the computation. And other use cases include that you can also mint ZK other tokens. We have seen ZK ETH, ZK USDC, and also ZK PayPay, and those meme coins. You can mint ZK tokens to ICP, do fast transfers among friends, use them daily, and then transfer them back to the main blockchain if you want to take it away in Ethereum. And also the usage also includes bridges and the cross-chain applications. A lot of things that you can do with the Chain Fusion. But in today's presentation, I'll be focusing on the use of the Chain Fusion technology for zero-knowledge proof verification for other blockchains like Bitcoin or Ethereum. Okay, so for people who are not that familiar with the concept of zero-knowledge proof, here's a very quick introduction. So we know ZK or ZKP has been in this Web3 ecosystem for quite some time. To very quickly define what it is, or to grasp the essence of this technology, I think you can just memorize this one sentence. Zero-knowledge proof is basically a proof of an honest computation without the need to re-execute it. So all you need to remember is that ZK is about computation integrity. That means somebody else runs some computation at their side in their own computer, in their own servers. Maybe it's a long and tedious computation. And what ZK can provide from my side is to verify the correctness of this computation without repeating it. So there are two main attributes of zero-knowledge proof. We call it a succinctness and zero-knowledge. Succinctness basically means we can verify a computation at a much lower cost in terms of resource or time than re-executing it. So I can verify if the computation that took place in other people's computer is correct or not without actually repeating the computation. This is the first feature provided by zero-knowledge proof called succinctness. The other feature is actually called zero-knowledge. So it means during this computation in other people's computer, they can hide certain things from me. For example, they can have some private input in their computation. I couldn't see them, but they can still prove to me that they have run a correct computation. So in this way, you can hide certain values for your computation and thus preserve the privacy of this computation. And technology-wise, we often see in industry that we have two flavors of zero-knowledge proof. The first one is called the zk-SNARK, and the second one is called the zk-STARK. I think people who are familiar with this field must have heard about these terms quite often. So for zk-SNARK, it has the benefits of a smaller proof size. The Groth 16 proofs are in the order, well, I think almost a similar size as the Ethereum transaction. So it's quite small, and it's very easy to verify at the smart contract level in the blockchain. One issue with the zk-SNARK is it usually requires a trust setup, which is long and sometimes criticized by the community, is that it's not that much decentralized process. So you need to do some pre-processing and trust setup for using a zk-SNARK. And to actually use the zk-SNARK to design the algorithm, what you need to do is design something we call it as a circuit. So if you have a background of electronics or computer science, you know that to execute a computation, what you could do is to use components and to form a circuit to run the computation. That's basically how zk-SNARK is used for writing your own computation. And on the other side, we have zk-STARK. So it's a totally different way to do zk, but it's also quite frequently used today. It has a bigger proof, or actually much larger proof than the zk-SNARKs. So what we have observed in some zk VMs today, they have a STARK proof of the size of 100 to 200 kilobytes per proof, which is very, very large. But the efficiency for zk-STARK is very high, which means the proof generation and verification usually takes less time, and it does not require a trust setup because they use a different cryptographic primitive called hashing compared to zk-SNARK. And we see that zk-STARK today are mostly used for a new thing that we call a zk-VM, which stands for Zero Knowledge Virtual Machine. So Zero Knowledge Virtual Machine works in such a way that we're basically using zk to prove the correctness of the execution of this virtual machine. And developers do not need to write their computation in the language of circuit. So what they could do is to write their computation in zk-VM specific languages, such as assembly language, or in better case, they can just write their program in the language that they are familiar with, like Rust or JavaScript. And the program that they write will be executed within this zk-VM, and a proof will be generated automatically for them. So in general, for regular application developers, zk-STARK-based zk-VM is the way to go for them, I'd say, for shorter development time and easier development effort. So this is a very quick overview of zero knowledge proof. And if we examine this field today, we see that the zk has some limitations regarding the existing infrastructure. As we have just discussed, zero knowledge proof offers benefits of trust and privacy. For trust, basically it means you can verify the computation without re-executing it. You can know whether other people were being honest when performing a computation. And for privacy, it means that you can hide certain secret data at the user side without exposing it to everyone. So it has all these benefits. But if we do zero knowledge proof verification in a blockchain like Ethereum, which is basically what people do today very often, and we see a lot of limitations. The most notable limitation is that zk is expensive and it's slow. As I just mentioned, so if it is a zk-SNARK proof, then it is okay. It's relatively acceptable if you verify it in Ethereum. But if it is a zk-STARK proof, which means we know that in Ethereum the gas fee will fluctuate depending on if the chain is busy or not, and also depends on the price of Ether. But generally speaking, verifying a zk-STARK proof, which is very large, in Ethereum will cost you hundreds of US dollars, even $2,000 of US dollars per proof. So it's very expensive, and it's slow because the blocks are generated in Ethereum for every 15 seconds. And the proof verification is hard to develop because the verifier, which runs in Ethereum as a smart contract, and it needs to be written in Solidity. So Solidity is not such a good language to program something to verify zk proofs, so it's hard to develop. And it lacks interoperability and composability in that your proof is verified in Ethereum. That means it can basically only be used in Ethereum. And if you need to use the proof in some other chains, for example, in Bitcoin or in Solana, a proof verified in Ethereum cannot help you. You have to do the verification all over again in other chains. In Solana, maybe it's okay. We don't do it personally by ourselves, but in Bitcoin, we know it's very, very difficult to verify a zk proof in that chain. Not impossible, but very, very difficult. So all these limitations make the use of zk technology a little bit difficult in the field. We know it has all these benefits for trust and privacy, and a lot of people are trying to include zk in their own solutions and products. But until today, it has been difficult to ship a zk-based product. So with all these problems, what we are proposing here from zCloak network is that we have a new product that we call Cloaking Layer. Cloaking Layer is universal zk verification infrastructure for all chains. So a very quick summary of its benefits. It's very fast. So what we have measured and experimented in the field is that we see sub-second finality because we run the zk verifier as native WASM code in ICP. So it's very, very fast when it comes to zk verification. It's very cost efficient, and the cost per proof, no matter it's zk-SNARK or zk-STARK, the cost is in the range of 1 to 2 US cents per proof. So basically you spend 1 cent per proof verification, which is a lot cheaper than doing the same thing in Ethereum or other chains. And it has a very good interoperability. Now here comes the concept we're talking today, which is ICP Chain Fusion. The thing is, after proof verification, you get a result for this ZKP. The result is either a pass or fail for the proof verification, so people will know your proof is correct or not. But this result is limited in the chain that does the verification. As I said, if we do it in Ethereum, the result stays in Ethereum. If you want to use the same result in another chain, you have to figure it out in the other chain. So it cannot be reused. But in the case of ICP, what we could do is that we can use the same chain or even the same canister for proof verification. And after the proof verification, we can write the proof verification results using the Chain Fusion functionality, basically threshold ECDSA or Schnorr signatures. We can just assign the result, whether it's correct or not, and just send the result to another chain, to Ethereum, to Solana, or to Bitcoin, so that any other chains can verify a signature and they will be able to know that if a certain zk-STARK proof is correct or not. So this is a very powerful feature that is provided by the ICP Chain Fusion. And currently we are working on multiple zk systems. We know that there are quite a lot of zk virtual machines and different proving systems in the space. We are having a Polygon Maiden, we have RISC-0, SP1, all these are already working in Cloaking Layer, by the way. We have Jolt, Nova. So all the systems that you are seeing today, most of them are designed using the Rust programming language, which makes them very easy to be ported to a WASM, which runs directly within an ICP canister, which is great. So yeah, we have this architecture that we have set up, which can accommodate not only existing zkVM systems, but we can also extend them for other new zkVMs in the future. We also have a tunable security and cost trade-off. which means currently the security of the cloaking layer is guaranteed by ICP. And we run the verification canister in one subnet. But in the future, if necessary, if it is required by highly security sensitive applications, we can replicate the same application in different subnets. So I'm not saying that we do one subnet replication, but the same application will take place in different subnets, which gives some kind of duplication, which will increase the cost, but also make the application much more decentralized and also secure. So we have this option to make a trade-off between security and cost. Okay, so here is a high-level system architecture of cloaking layer. So basically, we have struck a balance between decentralization, performance, and interoperability in ICP. What we're seeing right now in the center of this diagram is the ICP subnet. We see all these nodes or replica within this subnet. And within each replica, we have our application or verifier canister. And this canister is basically the cloaking layer canister. It holds several different zk systems verifiers within the same canister. So the user on the bottom left side can send either snark proofs or start proofs via HTTP calls to the cloaking layer canister. The proof will be verified by corresponding verifiers within the canister, and the result of the verification can be right to any target chain. So on the bottom right corner of this diagram, we can see that we have quite a few targeted chains that we can send the result to, including Bitcoin, Ethereum, Solana, and also we can use it in non-Web3 scenarios. We can send the verification result to an AI agent, which will drive the agent to do some interesting work. So yeah, this is a high-level overview of the architecture of the system. So basically, the most important component here is the canister that runs the zk verifier, and also the threshold ECDSA signature capability from ICP, so that we can send the result to different networks. Okay, so the use cases that we have thought about for cloaking layer are quite a few. Actually, if you look at the left side, we have the regular Web3 applications like zk rollups, zk bridges, zk coprocessors, and zk MLs. These are quite latest new topics using zero-knowledge proof. And we have also some other different field like payment or identity or DePIN. You can use it for gaming. You can use it for AI agent. So all the proofs generated with these use cases can be verified in the cloaking layer, and they can be signed using the Chain Fusion technology and sent to a targeted chain. So out of these applications or use cases, I'd like to pick one or two to discuss the latest progress that we have made so far. One very interesting field that we're seeing that has a lot of potential to use this cloaking layer functionality is actually DePIN. We have been talking to quite a few DePIN projects lately, so more than 20 of them, I think. And a lot of projects talked to us, and they actually realized that they have, at a certain stage of their project, they will have a privacy issue regarding the data that is collected by the device. We see DePIN projects that has hardware in a form of a ring. For example, you have a DePIN project that ship watches that you can watch and that detect your heartbeat or blood pressure, or if you're sleeping at night well or not. So all these metrics that they can measure on a person's body, so we call it biometric data that they collect from a person. These are highly sensitive information. And in many regions, if you upload this data directly to a centralized server or cross-border to another country, you need to watch out the data regulations in that region. We know the GDPR is enforced in Europe, and there are also similar data privacy regulations in Singapore, in China, and also in the United States, in a lot of other countries. So it usually is not okay for DePIN project to directly collect some data from from a person or from a company, from a spot, and upload it to the cloud or to a public blockchain. So what they could benefit from Cloaking Layer is that they usually use this data for some sort of computation. Maybe they want to compute some scores about this person. Maybe they want to analyze certain parts of their biometric data and get some conclusion. So basically, this is what they want. And what zk can help here is to run a zk computation within the device, within the person's phone or within their watch, for example, which means the computation of private data will take place at client side, which means it takes place in the person's phone or in their physical device that they're wearing. The data is never uploaded to a cloud or to a public blockchain. So in such case, we can definitely preserve the privacy of the person because their private data has never been uploaded to any other place. They always stay local in their own device. So we can say in this case, we absolutely preserve the privacy of the person. And Cloaking Layer can help to verify the computation that takes place in their local device to make sure that it's actually a correct result that they're uploading, they're not cheating or anything, and they can use this result in any targeted chain that they prefer, maybe in Solana, maybe in Bitcoin, to claim a reward or participate in some sort of computation. So there are a lot of things they can do with this. So this is a very interesting use case we have observed with DePIN. And another interesting use case we're seeing is with the payment. We're actually collaborating with a payment company right here in Singapore, which deploy this POS machine, point of sale machine. They have this POS machine network and they have all the payment transactions that is going on in this POS machine. And by the regulation here, it is not possible to upload the payment data to a public blockchain because it contains a lot of credit card and consumer privacy in those data. So you definitely cannot upload it to third parties, but they also rely on this transaction data to do some sort of a computation, maybe for calculation of a score or something for rewarding the users. So in this case, what we have done is we help to implement a zk program using zkVM within the POS machine themselves and in their servers. So what happens is, again, the calculation on the private transaction data take place locally in their own device. So without sending the data to a public blockchain or public cloud, you will be able to do computation on this data and get and generate zk proof to prove that your local computation is actually correct. And this ZKP that's generated is verified by the Cloaking Layer. The result is sent back to Bitcoin or to Ethereum. So it's a very versatile. And yeah, so what we also want to do actually today is to welcome people to build with us and to use this Cloaking Layer functionality and the ZKVMs that you're seeing on the market to come up with some innovative ideas and to use the ICP Chain Fusion functionality to make it a multi-chain zk application. Here is a summary of the advantages of the Cloaking Layer compared to doing zk verification in Ethereum. We know zk has been in the field in the Web3 industry for quite some time, but we're not seeing that many applications. One of the core reasons we think was that the verification of zk proof is just too expensive and not so convenient right now because it's limited to Ethereum. It's limited, it's very expensive and slow. So it's not ready for everyday use. But with the help of Cloaking Layer, we're cutting the price for zk verification to 1 or 2 US cents. We're making it very flexible. We're making the result available for all chains thanks to Chain Fusion. And also there's another interesting feature from ICP. It's called reverse gas fee, which means the user themselves who use the ICP chain, they do not pay the gas fee. It is the application developers, basically us, we're paying the fees for zk verification, which is good for the users because they are not going to use any specific tokens to do zk verification. Actually, right now, the use of a cloaking layer is completely free. So the user will not see any tokens whatsoever. The only thing they need to do is to throw a ZKP generated in their server, generated in their watch or in their phone to the cloaking layer, get the result verified, and shoot it to another chain. So in this process, basically they see no gas token from ICP, and the service to them is just like any Web2 service they can see. And yeah, so a lot of benefits for using the cloaking layer for proof verification. And this is a quick roadmap from our side. So the cloaking layer is in testnet stage. Already, we have integrated the 4 or 5 zk systems within it. We have got the system working very interestingly with the small DePIN devices. We have something that's it's called a Raspberry Pi, basically an embedded computer on a credit card size circuit. It's not very powerful, but it is powerful enough to generate ZKP locally in that board. And the ZKP that's generated in that very small computing board is sent to the cloaking layer, get verified, the result is sent to Solana chain. So we can do all the DePIN verification using cloaking layer. And next year, we're also enhancing this traceability of cloaking layer using some other fancy techniques like dual staking, or maybe even explore the Bitcoin AVS system for extreme security. So these are things that we're doing next year. And regarding to this topic, we know that ICP Chain Fusion technology is very helpful in the cloaking layer project, in that we can send the result of the zk verification to any targeted chain that we like. And especially when it comes to Bitcoin, the interesting things that we can do with zk and Bitcoin are a lot. So here are some quick ideas that we have come up with. For example, you can do fund custody using ZKP for unlocking, which means you can use ZK for any sort of computation. And the result of this computation can be used to unlock some fund in the Bitcoin network. And we can also use ZK for gaming. For example, there are quite a few ZK games on the market. Maybe when you walk out of a maze and defeated some enemies, you can generate ZK proof for that and claim some reward on the Bitcoin network. You can do lottery, so you can prove to other people that you have won a lottery without showing the details or the cards, for example, in your hand, and you can prove it to the Bitcoin network and to get your reward. We can do ZK ID, so basically you can prove certain things about yourself, your credit score, your identity, your nationality. So is your income within a certain range? Things like that. And all these things can be used to drive some fund transfer or fund unlocking in the Bitcoin network. So yeah, as I already said, that we hope people will find this cloaking layer functionality interesting, and we look forward to be building with everyone. Okay, so here's basically the end of my presentation, and here is the contact information about myself and about my project. So now I will end the presentation.
I'm going to invite them back onto the stage. I think they left temporarily.
You heard I finished till the end of the presentation?
Yes.
Okay.
Yeah. It only ended when you shared your last slide with
Great.
the contacts. And if you could actually get that up again,
yeah,
that would be really good as well.
Okay, so I was saying that we have a quick video demo that we want to share with the people. Shall I do it now? Okay. Okay, I guess you can see it already. Okay, so here's a quick demo. It's on Ethereum. We're working on the Bitcoin version. So it's a ZK payment application. basically what happens is that I'll tell a little bit background about this application. So we have all the stable coins and other coins on Ethereum. Sometimes we want to transfer our coins to our friend or for buying things, and we don't want other people to know that it is us who have spent this money or when and how much. So we want to preserve some sort of privacy. So what we can do is using the app that we have developed. It's called zkPay. It uses the cloaking layer that I just talked about as a verification layer, and the result can be written back to Ethereum. So it's the Ethereum-based zk payment application that we have developed. So right from start, what we will do right now is to deposit some USDC from Ethereum to this zkPay application. It's basically a zk payment layer on top of Ethereum. And what happens right now is you deposit your USDC into a smart contract that we have developed, that we have deployed on Ethereum. So basically your USDC is locked within that smart contract. Meanwhile, the same amount of USDC called the zk USDC is minted on the zk payment layer, as you will see very soon. Okay, so your fund in Ethereum is locked, and you have 100 zk USDC in the zk payment layer. And if you look at the Explorer, you will be able to see the transaction is successful, and you will be able to see that from the chain level, you have actually transferred 100 USDC to our custody smart contract. So the fund is locked, and you have some fund in the zk payment layer. Now what we can do is to switch to another account. We call it account 2, and we connect it to our application. You can see that balance is 0. And now the account 2 is the receiver of the fund. I will generate something like an invoice in a business, e-commerce business. So what is happening now is I'm generating an invoice of 50 USDC, and I'm sending this invoice to account 1. So the invoice has been sent. If I switch back to account 1, what I will be able to see is that we received an invoice to be paid. We check it, and we can actually pay it at the zk payment layer. So the fund can be paid, and the money will be deducted from our current balance. Okay, so the balance here now is already 50, and the other 50 is sent to account 2, but not through the Ethereum network, but through the zk payment layer. So you see the receipt here, and it's already paid. What you can do is to redeem the money that is sent in the zk payment layer. So account 2 now also have 50 within their zk payment layer. So they now have 80 USDC in the mainnet, and now they want to withdraw. So I'll accelerate this a little bit. This will be further improved with our algorithm to make it faster. So basically what is happening right now is account 2 is withdrawing the 50 USDC from the zk payment layer to the Ethereum mainnet. So once that happens, you will be able to see that they have a balance of 130 USDC in their wallet. Okay, here's the Explorer. You can see the fund has been transferred, it's successful, and indeed 50 USDC has been sent to the recipient account, and currently they have 130 USDC in their wallet. Okay, yeah, here's the flow. Okay, so that's basically it for my presentation and the show of the demo. If there's any questions, I'm happy to answer them.
Thank you for the lovely demo. I think there is one question from Mert, which is, what is the best way to get started with Lightning?
Okay, so personally, I do advise following the tutorials on the official website of a Dfinity. They have a very comprehensive documentation, and also there's a video series for beginners to get started building stuff. I'd highly recommend that. It has helped us a lot.
I think there is no more questions. In that case, I will take the opportunity to remind people again to join the ICP Chain Fusion Hackathon Bitcoin edition. Everything that you have learned in this Educate series can be very much so applied in the hackathon, and there are great bounties to compete for. So keep an eye on our website for that. And thank you everyone for attending as well. And thank you again, Xiao, for the lovely presentation as well.
Thank you. Yeah, good luck to everyone for your hackathon. Hopefully to see your great work there. Okay.
Oh, I might, thank you. I thought someone was going to ask a question. Okay, great. Thanks everyone. Bye-bye.
Thank you.